Let's summarize today about what we have done last time about the Carnot cycle. So Carnot, it's a reversible cycle, as we said. When we said actually as the cycle is reversible, so it can be applied for heat engines to convert the heat into work, and it can also apply for refrigerators or air conditioning. They have the same meaning, or the case actually when we have an air conditioning system working as a heat pump in this case. So the cycle can be applied for heat engine to convert heat into work, or it can apply for a refrigeration or air conditioning system to convert, in this case, work into control on the amount of heat transfer, either heat absorbed in case actually or air cooling load in case of refrigeration or air conditioning system, or actually the heat rejected in case when we are talking about a heat pump in this case. Like we said, the thermal efficiency, we evaluate the performance of a heat engine using the thermal efficiency, which is equal to the network output divided by the heat added to the system. Or it is equal to work net is equal to the same as Q net. So this is actually for the Carnot cycle. This is actually as the system working on a cycle. So in both cases, actually for heat engine or refrigeration cycle, we have Q net is the same as work net. Q net, which is Q high minus the difference between Q high and the Q low. And we said in case of Carnot reversible cycle, heat is added or rejected as function of temperature at constant temperature. So that means the heat is a sole function of the temperature. And based on this, we said for a Carnot cycle, we can say the ratio of Q high over Q low is the same as T high over T low. And Shabab applies either actually for the heat engine, and both of them applied for the refrigeration and heat pump system. Type work net is the same as Q net, which is Q high minus Q low divided by Q high, and that should equal to 1 minus Q low divided by Q high. And we said this thermal efficiency for any actual heat engine or reversible heat engine, even for the case of Carnot cycle, should be less than 100%. And this is based on the second law of thermodynamics. But this is the actual efficiency. What about the Carnot one? We call it either thermal reversible, or we call it actually as the maximum efficiency. As the efficiency is maximum, we don't have losses within the system. That should equal to work net maximum divided by Q high minimum. So if he asked you to calculate the thermal efficiency for minimum heat input to the system, that means the thermal efficiency is maximum in this case. And in this case, we can just replace Q high over Q low by T high over T low. This relationship only applied for the maximum efficiency, and that should equal to 1 minus T low divided by T high in this case. Okay, this T low should be, or T high. T low is the temperature in case of heat engine, is the temperature of the heat sink in which actually the condenser rejects the heat at low temperature. T high is the temperature at which actually is the source of the boiler, the source of the heat transfer to the boiler, which actually boils steam in case when we have a steam power plant as an example for a heat engine. Okay, and that should be also substituted in Kelvin in this case. Okay, right, this is regarding the heat engine. Also the same for the case of refrigeration or heat pump system. So for the case of refrigerator, when we have a refrigerator, we call it also as air conditioning is working also on the same cycle. So in case of refrigerator or air conditioning system, we evaluate the performance using the coefficient of performance of the refrigerator, which is equal to what we need from the system is the cooling load. We call this Q low as the cooling load, the load required to be cooled down. Okay, like a food compartment in case of refrigerator, or actually the amount of heat that we need to absorb from the air to cool down the air in case of air conditioning. That is equal to the cooling load, Q load, divided by the network input to the system, which is the work input to the compressor. Okay, this is the coefficient of performance. Work net is the same as Q net, so it will equal to Q low, the same as Q high minus Q low. Okay, What about the maximum coefficient of performance of the refrigerator? We call it reversible or maximum. That should equal to actually Q low divided by also working it. But this Q low is maximum and the work input to the system is minimum in this case. Okay? So if he asks you to calculate the coefficient of performance for minimum work input to the system, that means this coefficient of performance is maximum and the system is working on Carnot cycle. Like this, if he asked you to calculate the coefficient of performance for maximum cooling load, maximum Q low. So in this case, the coefficient of performance is maximum. And in this case, we can replace Q high over Q low by T low over T high in this case. And we can express this coefficient of performance as function of temperature will equal to T low divided by T high minus T low. So this is the maximum coefficient of performance, and this is the actual, how we define the actual coefficient of performance. This is the actual thermal efficiency, and this is also the maximum thermal efficiency. The mean difference, this work is maximum, this input is minimum, and we can express actually, we can replace the heat transfer ratio by the temperature ratio. I will prove this relation for you just right now. I will prove to you actually why we have, in case when we have a Carnot cycle, the ratio of heat transfer Q high over Q low is the same as T high over T low. Right, this is regarding the refrigerator. What about of the heat pump? Heat pump is the same cycle, but what we need from the system is heat rejected, Q high, not Q low in this case. Okay, so in case when we have a heat pump system, so in this case we evaluate the performance also using the coefficient of performance in this case. So for the case of heat pump is actually air conditioning system, but we just flipped it to have the condenser inside and the evaporator outside. Like when we are in the winter or something, in this case, we absorb the heat from outside. The evaporator will be outside to absorb the heat from the air outside, and then it can reject the heat to the room inside to heat up the room. So we call the air conditioning system in this case as heat pump. But the coefficient of performance of the heat pump is equal to Q high, the heat rejected from the condenser, divided by the net work input to the system. Q net is the same as actually work net, which is, we can replace work net by Q high minus Q low in this case. Okay. But in case when we have a heat pump working on a Carnot cycle, we can call the coefficient of performance of the heat pump as the reversible, as we said, or the maximum one. It will equal to Q high divided by work net. But this work net in this case will be minimum. This Q high is maximum in this case. And that also should equal to Q high divided by Q high minus Q low. And we can replace Q high over Q low. If I divide it by up and down, then we can replace Q high over Q low by T high over T low. That should result in maximum coefficient of performance will equal to T high over T high minus T low. And this is the maximum coefficient of performance of a heat pump, and this is the actual one. So actual maximum. The difference is that we have replaced the heat transfer ratio by the temperature in case when the system is working on the Carnot cycle. But we have here two Carnot principles. We have for any system working on a Carnot cycle, any system, the efficiency of any irreversible or actual heat engine. Any actual heat engine should have efficiency that should be less than the reversible one. As we said, the Carnot cycle gives us actually the maximum efficiency of the system because we assume we don't have any kind of losses. Okay, but this is actually in case when we compare irreversible or actual heat engine with a reversible heat engine, the efficiency of the actual one should be less than the efficiency of the reversible heat engine. But the second Carnot principle is that if we have two reversible heat engines working between the same T high and the same T low, they should have the same efficiency. And that is clear from here. If we have two heat engines and we have the same T high, same T low, that means actually the coefficient of performance should be the same in this case. So if two reversible heat engine, not actual, because the actual may have some losses, and one of them is bigger than the other, so in this case the efficiency will be different. But if we have two systems, two reversible systems, working on Carnot cycle for the same T high and T lows, we should come up actually with the same maximum efficiency in this case. And based on this concept, we can prove the relation that Q high over Q low is equal to T high over T low. We call this actually as thermodynamic temperature scale, based on which, if you remember, we said we assign the temperature equal to 0 Kelvin when the absolute pressure is equal to 0, absolute vacuum in this case. And in this case, the temperature is only function of the heat transfer, not function of the property of any fluid. We said in the Celsius scale, we take the properties of water, boiling point of water, as a reference point. And based on this, we get the scale. But actually, for the thermodynamic temperature scale, it does not depend on the property of any substance. It is only function of the heat transfer. And we assign the value of 0 Kelvin when the temperature, when the absolute pressure is equal to 0 in this case. Okay? And we develop this relation early in chapter 1, temperature in Celsius equal to temperature in Kelvin plus 273. And think you know about this. But what we need actually right now is just to prove that Q high over Q low is the same as T high over T low. So let's consider we have a source here existing at a high temperature. So let's consider this high temperature. I will name it as T1. Okay, so this is T1. And we have a sink here at temperature, let's say T3. And we have two reversible heat engines between the same T1 and T3. So they should have the same efficiency. One heat engine consists actually of two consecutive heat engines, let's say heat engine A and heat engine B in this case. The heat engine A takes Q temperature source T1 and gives actually converted to work, let's say the produced work from the system A is work A, and reject some heat, which is, let's say, Q2, okay? This rejected heat from the system A is absorbed by B, and then B actually produce work, let's say work B, and reject actually Q3 to a low temperature sink at T3. This is one system, consists actually of two consecutive systems. Both of them are reversible. So this one is reversible, and this one is reversible, okay? We have in parallel here one system, only one system, let's say system C, that takes the same amount of heat Q high Q1, because we have the temperature is T1, so it will be the same as Q1, and reject here the same amount, which is Q3 to a low temperature sink at T3. And this system is also reversible. But we said if we have two reversible heat engines between the same high temperature and low temperature, they should have the same efficiency. That means the combined efficiency of the system AB between T1 and T3, that should equal to the efficiency of the system C. This efficiency of A and B will equal to the efficiency of A multiplied by the efficiency of B. The combined efficiency of both of them is the multiplication. That should equal to the efficiency of C. Times the efficiency of A, which is a heat engine, will equal to 1 minus Q low, which is Q2, divided by Q high, which is Q1, multiplied by B, 1 minus Q low, which is Q3, divided by Q high for B, which is Q2. That should equal to the efficiency of C, 1 minus Q low, which is Q3, divided by Q high, which is Q1. Okay? That means here we have this term is function of Q2 and the Q1 multiplied by function of Q2 and the Q3, that equal to a function of Q3 and the Q1. Look at the right hand side term, it is independent of Q2. Only we have Q1 and the Q3. This is mathematically equal to another two functions. Both of them are function of Q2 and the Q1 and the Q3. So that means this term also, as the right hand side term is independent, this term is not function of Q2. That means this term also, the left hand side, should not be actually function also of Q2. So that term also should be independent of Q2. Okay? This is one relation. We said in case of reversible heat engine, heat is added or rejected at constant temperature. That means in this case, heat is a function of temperature. So that means this term here, function of Q2 and the Q1, this term also is function of T1 and T2. multiplied by function of Q2, Q3, which is T2 and T3. That should equal to a function of Q3 and Q1, which is function of T3 and T1, as the heat is added at constant temperature. So heat is function of temperature, okay? And this is equation number 2. This term is not function also of T2, only T1 and T3. And this term should also not be a function of T2. However, we have this term is function of T2 and this term is function of T2. But when we multiply both of them, they should come up mathematically as independent of T2, as this term is not function of T2, and we have this term is equal to this term. So we have this relation based on equation 1 and 2. They cannot be achieved mathematically unless we have the ratio between Q1 over Q2 is the same as T1 over T2. And also, it cannot be achieved unless actually Q2 over Q3 is the same as T2 over T3. And also Q3 over Q1 is the same as T3 over T1. Or we can generalize the case, then we can say Q high over Q low will equal to T high over T low. And this is for the case, only for the case when we have a reversible heat engine. For a reversible heat engine, the ratio between Q high over Q low is the same as T high over T low. And this is how we prove this relation. طيب here شباب what we said in case of a reversible heat engine, if it is actually between T high and T low, have efficiency equal to 70%. This is the maximum efficiency. So if we have irreversible heat engine, actual one, it should have efficiencies that should be less than the reversible one. So the thermal reversible for irreversible heat engine, the efficiency should be less than the maximum efficiency or the reversible efficiency. But is it possible to have efficiency greater than the maximum efficiency? No. So if somebody give you a heat engine, provided you a heat engine, he said we have a heat engine with efficiency equal to 80%, and you calculate the maximum efficiency, found it equal to 70%, that means actually this engine is impossible engine. This engine cannot give this efficiency. So it is impossible in this case. And if it is reversible, this is not an actual case, just it is non-real case, the efficiency in this case will equal to the maximum efficiency of the engine. Type the maximum efficiency is equal to 1 minus T low over T high. How we can increase this efficiency? We can increase the maximum efficiency by actually increasing the quality of the energy in this case. Quality of the energy is mainly function of the temperature. So if we have a system at higher temperature, that means actually this system has higher quality of energy. Let's look here for the same Q low. If we increase the value of T high, which is function of the heat added to the heat engine. So if we increase the heat added to the engine at fixed heat rejected, so in this case, the value of high temperature T high will be increased in this case, and as the value of T high increase, the maximum efficiency, which is 1 minus T low over T high, will be increasing in this case. So T high is 350, the efficiency is 13.4. When we increase it to 925, the efficiency will approach 67.2. So the energy has a quality like a quantity, but this quality is a function of the temperature. As the temperature increases, as the quality of the energy increases in this case. Type here we have, he said we have a Carnot heat engine. Carnot heat engine, that means the efficiency is maximum, and we can express this efficiency as function of temperature in this case. He said this heat engine receives the heat 500 kilojoule from a source, temperature source that is existing at 652 degrees C. So this is T high. The source for the heat engine is the high temperature. So this is T high 625 degrees C. Okay, and reject the heat to a low temperature sink at existing at 30 degrees C. So the sink in this case at which the heat is rejected is equal to the temperature is equal to 30 degrees C. Now we have T high and T low, then we can calculate the efficiency of this system, which is the maximum efficiency. Okay, type we need to calculate the efficiency. We have calculated for this Carnot heat engine, and we need the amount of heat rejected. We have for a Carnot heat engine, we have Q low over Q high is the same as T low over T high. We have in this case, he provided us with the value of T high, which is Q high, sorry, which is 500 kilojoule. We have T low and T high, then we can substitute to get Q low. Just keep in mind that the temperature should be in Kelvin in this case. Yani, this is a simple example. I will just provide you, inshallah, I will solve with you right now a little bit a complicated example. But in case of refrigeration cycle, as we said, the coefficient of performance for the reversible cycle should be the maximum. And for the actual one, it should be less than the maximum. And it is impossible actually to design a compressible refrigeration system that have coefficient of performance that is greater than the value obtained by the Carnot cycle or the reversible one. Okay, this is what we said. Also, شباب, the refrigeration and heat pump system, this coefficient of performance is function of T low. As we reduce the value of T low, then in this case, the coefficient of performance for the heat pump or for the refrigeration system will be reduced in this case. So it is not good, شباب, to reduce the temperature much, reduce the temperature of the fridge at your home. If you reduce the temperature of the freezer to be actually at the minimum value, that means actually this system will require more work input to the system in order actually to get this temperature. And in this case, the fridge will be consuming more electrical power in this case. Like this, also the air conditioning system, it is not advised actually to reduce the temperature out of the air conditioning system much to be actually much low value. It has to be reasonable value, because as you reduce the value of T low, the temperature of the evaporator inside the evaporator, in this case, actually, it will require more work input to the compressor, and it will require more electrical power in this case. So for the air conditioning system, the green operation, it should be around 23, 24 degrees C. That should be fine in this case. And also for the freezer, you should not go actually to very low temperature. So that actually the freezer, the fridge cannot actually consume much amount of the electrical power. Here is also a kind of simple example. He said we have a heat pump system. Heat pump, I have to repeat this again. His pump is an air conditioning system, but just I flipped it to have the condenser inside and the evaporator outside. Condenser inside the room. He said we have a house. This house actually in the winter is rejecting heat, is losing heat to the surrounding at a rate of 135,000 kilojoule per hour. Okay, so this heat is lost. Now we have to fix a heat engine in order actually to substitute this heat. It will provide, the condenser will be inside, so it will reject the heat to inside with the same amount, so that we can keep this house as the temperature equal to 21 degrees C. So when he say we want to maintain this house at this temperature, and this house is rejecting this heat, so that means the heat pump will be actually compensating for this heat rejected in order to keep the temperature constant. So this should be Q high in this case. And the house is maintained at temperature 21. That should be T low or T high. We said for a heat pump, we just get the condenser inside. So that means T high is inside the house. So this temperature 21 is the high temperature. And he said the outdoor temperature, which is the sink temperature from which actually the source of heat, from which we absorb the heat to inside. He said actually the outdoor is existing at temperature equal to -5 degrees C. -5 degrees C in the winter, this may be in North America or something. So in this case, this is a real situation. So in this case, we absorb the heat from this -5 degrees C atmosphere through the air conditioning system, which is working as a heat pump, and reject this heat inside the house in this case. So now we have T low is equal to -5, T high is equal to 21 degrees C in this case. And we need to determine the minimum power required to drive the heat pump. Minimum power required to drive the heat pump, that means the heat pump in this case is working on a Carnot cycle. And this system actually is a reversible system in this case. Okay, so in this case, he said we need to calculate the coefficient of performance of the heat pump for minimum work input. So the coefficient of performance of the heat pump is equal to Q high divided by the network input to the system. If this network input is minimum, that means this coefficient of performance is maximum, or we call it reversible. That means this cycle is working on the Carnot cycle. and the coefficient of performance, we can express it in this case as function of temperature will equal to T high divided by T high minus T low. And this is this is here we can substitute. So the coefficient of performance will equal to T high. It is the same, yani just I divided by T high up and down. Then you can substitute, but you have to substitute the temperature in Kelvin in this case. Then we can get the coefficient of performance 11.3. And in case of reversible heat engine, or any heat engine actually, we define the coefficient of performance is equal to Q high divided by work net. This is Q high divided by work net. In this case, we have Q high is given, and we have in this case, we have calculated the coefficient of performance. So the coefficient, the network input to the system will equal to the network will equal to Q high divided by the coefficient of performance. Then yani, we can substitute this. What I want you to understand from this situation is to understand actually which value is T high and which value is T low. He said in this case we have a heat pump, which is air conditioning system that we have flipped to have the condenser inside for the system to work as a heat pump. So when he says a room or the house is maintained at 21 degrees C, that means actually this is the temperature of the sink for this heat pump, at which actually this heat pump rejects the heat. So this should be T high in this case. And the outdoor temperature should be T low, because the evaporator will be outside in this case. Okay. This is a simple example you can look at, but let me just solve with you here an example. This example here. This example from a previous exam. We can just solve it together. So let's look here. Let's see here how we can solve this problem. As I told you, I just went through this simple solved problem because it gives you Q high or Q low directly without just getting you into any other detailed calculation of Q low and Q high. But let's look here. If we have a refrigeration system, we have in this case, we have a refrigerator. So when he tells you we have a refrigerator, so you have just directly, you have to draw this actually the cycle for the refrigeration system. So the cycle for the refrigeration system, we have expansion valve, we have evaporator, and then we have a compressor. And at the top here, we have the condenser in which actually heat is ejected and cycle is going actually in this direction. This is actually the refrigeration cycle. He said this is a kind of big refrigeration cycle. In case usually if a refrigeration cycle like the fridge, small fridge or something, this fridge, the cooling load is low. So in this case, the heat rejected, we can just reject it to the surrounding air. So just we have set of wires, set of tubes, we pass the freon inside, then actually we increase as we use actually more tubes, we increase the surface area subjected to the air. So in this case, the heat will be rejected, Q high will be rejected to the surrounding air. So the surrounding air in the kitchen in this case can cool down the condenser, and it can convert it from the vapor phase to the liquid phase in this case. And this is the evaporator, heat is added, Q low, we call Q low as actually as the cooling load in this case, okay? But in case of if we have big refrigeration system, which is used actually in freezing the fruits and something in big markets in this case. So in this case, actually, the air may not be able actually to cool down the freon in this case. So in this case, we can use the cooling water. We can use here circuit of cooling water. So we can have cooling water is coming in, let's say at cross section, this is 1, and it is leaving actually at, let's say, cross section 2. So the heat in this case will be absorbed by the cooling water. So the heat will be rejected from the refrigerant. We have refrigerant 134 is the only refrigerant we have tables 4 in this course, is passing inside the condenser, which is coming at the vapor state, and it rejects the heat Q high to the cooling water, so it will be converted in this case to the liquid. Then we can pass it through the expansion of the throttling valve to reduce its pressure and temperature. Then we can repeat the cycle again to absorb the heat from the food compartment in case of a refrigeration system, or in case actually of air conditioning system, it can absorb the heat from the flowing air around in this case, and the cycle is repeating in this case. طيب we see that this condenser, we have cold fluid, which is cooling water that absorbs the heat from the hot fluid, which is the refrigerant. This is a kind of heat exchanger. This is exactly a heat exchanger in this case, which we have learned how to apply the first law of thermodynamics for a heat exchanger, as we have learned in chapter 5. So the Freon here is coming, let's say, at cross section 3, and it is leaving here at cross section 4. Water is coming at cross section 1 and leaving at cross section number 2 in this case. He given this example, we said we have a refrigeration heat engine is used actually to keep a refrigeration space. The refrigerated space is kept actually as minus 35 degrees C. That means actually the refrigeration space around this evaporator is left actually at low temperature equal to minus 35 degrees. So that means this temperature is T low. The temperature of the source of heat is given in this case, the temperature inside the evaporator. Okay. He said the cooling water, this cooling water is coming at step number 1 at 18 degrees C, and it is leaving actually at temperature equal to 26 degrees C. So it is leaving at 26 degrees C at step number 2. Okay. That is liquid water, okay. So it is enough actually to give you only the temperature T1 and T2, because the state is subcooled, and in case of subcooled actually at low pressure, we don't have subcooled table, we assume that the enthalpy will equal to H fluid at the given temperature from table A4, okay? Or we can consider it as liquid incompressible substance. We can say delta H will equal to CB multiplied by delta T, and CB we can get from table A3 in this case, okay? So those are the conditions of the cooling water. Regarding the refrigerant, he said this refrigerant is coming at state number 3 at pressure equal to 1.2 megapascal, and temperature is equal to 50 degrees. Okay, so the temperature at state 3 is 50 degrees C, and the pressure is 1.2 megapascal. Usually it is phase change process from the saturated vapor to saturated liquid. Okay, so that means the process almost will be done at constant pressure. He said here the pressure at 0.4 is the same as 1.2 megapascal, but he said the temperature is subcooled by 5 degrees C. So if you remember on the temperature PV diagram, this is the saturation curve. This is the line of constant temperature. This is the saturation temperature, and this is the saturation pressure. He said here the temperature of the flow that is leaving the evaporator is converted from vapor to liquid. So we are proceeding in this direction. He said the temperature at the exit of this condenser is subcooled by 5 degrees C. That means we get here subcooled by 5 degree difference between the saturation temperature and the temperature at the final state T2. So that means the temperature T2 at the exit of T4, we call it 4. So this is 4. Okay. So the temperature T4 is equal to the saturation temperature at this pressure, which is 1.2 megapascal, minus 5 degrees C, because he said it is subcooled by 5 degrees C. So the temperature T4 at the exit of the condenser is less than the saturation temperature at this given pressure by 5 degrees C. Okay. If you get the saturation temperature at this given pressure, this is a Shabab refrigerant, so pressure table, so I can go to table A12, you can get this saturation temperature, you'll find this saturation temperature is equal to 46.3, so the temperature T4 will equal to 46.3 minus 5, so it will actually equal to 41.3 degrees Celsius. So this is the temperature at 0.4 and the pressure at 0.4, and this is the idea initially. So if he told you the temperature is subcooled by 5 degrees C, that means the temperature at the outlet is less than the saturation temperature at this given pressure by 5 degrees C. Now we have the pressure and temperature of the refrigerant at the inlet of the condenser. We have the pressure and temperature at the outlet of the condenser for the refrigerant. And we have the temperature inlet for the cooling water, temperature outlet for the cooling water. He said actually the cooling water is flowing at a rate equal to 0.25 kilogram per second. So the mass flow rate of the cooling water, M dot cooling water, is equal to 0.25 kilogram per second. and we need to calculate the mass flow rate of refrigerant. So it is a heat exchanger in this case. We have the mass flow rate of the cold fluid, and we need to calculate the mass flow rate of the hot fluid. So if you remember, we said in this case, the heat, in this case, Q high, the heat is Q high, the same. Heat rejected by the refrigerant is the same as heat absorbed by the water, which we call it Q high in this case. So Q high in this case will equal to M dot water, which is the cooling water, multiplied by the enthalpy, which is actually H2 minus H1 in this case. We call it Q high, the heat absorbed by the water. Type, the mass flow rate of the cooling water is given, and we need to calculate H2 and H1. H2 and H1, he gave you T1 and T2, and the state is just liquid water. So in this case, we can get the temperature T1, and in this case, we can just go to table A4. Then we can get H1 will equal to H fluid at the given temperature. In case of subcool, the enthalpy is equal to H fluid at the given temperature, not given pressure. Okay. So we can calculate the value of H1, and also like this T2, which is equal to T2 is equal to 26, T1 is 18. From table actually A4, we can get H2 will equal to H fluid at this temperature, which is 26 degrees C. This is 18 degrees C. Then we can get H1 and H2. We have the mass flow rate of water is equal to 0.25. Then we can substitute here to calculate Q dot high. Okay. You can just check on these values. Let me just. So here it is. So the mass flow rate will equal to 0.25 multiplied by 109 point something, which is H2 minus the enthalpy H1 will equal to 75. Then in this case, you can calculate the value of Q high, which will equal to 8.36 kilowatt. Okay, this is kilojoule per kilogram, and this is kilogram per second, so it should be 8.36 kilowatt in this case. But the heat absorbed by the water, it should be the same as the heat rejected from the refrigerant, and we need to calculate the mass flow rate of the refrigerant. So this Q high is also equal to, based on the heat exchanger, mass flow rate of the refrigerant multiplied by the difference in this case, which is H3 minus H4. At point 3, we have pressure is given for the refrigerant 1.2 megapascal and 50 degrees C. Shabab, 1 and 2, this is water. I used the steam table, table A4. 3 and 4, we have refrigerant. So I will be using refrigeration table from table A11 up to table A13. So at the temperature T3, at point 3, we have P3 is equal to 1.2 megapascal. T3 is equal to 50 degrees C. Then in this case, you can go check the status, pressure and temperature, go get the saturation temperature, compare it with the given temperature. I think in this case, it should be superheated. I will be using table A13. Then we can get the value of H3. Okay. For point 4, we have B4 is the same as 1.2 megapascal, and we have the temperature T4 is less than the saturation, which is actually subcooled. For he said it is subcooled by 5 degrees C. So we know the situation actually is subcooled. Subcooled, we don't have subcooled table for the refrigerant. So in this case, using this temperature, I will be going actually to table A11, then H4 will equal to H fluid at this given temperature, not given pressure. I have to repeat this again. There is a big difference. So the enthalpy H4 will equal to H fluid at the given temperature from the temperature table, table A11. Then we can get in this case the value of H4. But we have H3, H4, Q high we have calculated, which is the heat absorbed by the cooling water. Then we can calculate the mass flow rate of the refrigerant. You can check on this value. It will equal to 0.0498 kilogram per second in this case. Type, this is regarding the first requirement. It was a final problem exam, by the way. We need to calculate the refrigeration load. Refrigeration load, which we call it actually, which is Q load, is the refrigeration load that is required to be absorbed, the heat that is required to be absorbed from this system. How we can calculate Q load? He gave us in this problem that the network input to the compressor is equal to 3.3 kilowatt. So in this case, we have, as the system is working on a cycle, so Q net is the same as work net. Work net, which is the work input to the compressor, which is equal to 3.3 kilowatt. This is given. But this Q net is Q high minus Q low. We have just calculated Q high, which is equal to 8.36 minus Q low equal to the network input, which is 3.3. Then we can calculate, in this case, the value of cooling load. Q low, you can just calculate it will equal to 5.07 kilowatt in this case. So this is Q low in this case. Okay. But he asks us also to calculate the coefficient of performance. So the coefficient of performance for a refrigerator is equal to Q low divided by the network. Q low is 5.07 divided by the network, which is given here, 3.3. So the coefficient of performance, if you calculate it, will equal to 1.54. So the coefficient of performance can be greater than 1. Can be greater than 1 or less than 1. But the efficiency in case of heat engine should be actually less than 1. But this is the coefficient of performance. Now, he asked us, he said for the same cooling load, for the same Q low, we have the same value of Q low, calculate the minimum work input to the compressor in this case for this refrigeration system. So the coefficient of performance is equal to Q low divided by work net. He said now, let's assume this system is working to have minimum work input. That means this coefficient of performance is what? Will be maximum in this case. And the system will be working on a Carnot cycle. So the coefficient of performance of the refrigerator, reversible or maximum, is equal to T low divided by T high minus T low. That should equal to Q low divided by the network, which is actually minimum in this case. So if he asks you for the minimum work input, that means the coefficient of performance is maximum in this case. Okay? And we can express it in terms of the temperature. But in this case, Shabab, where is T low and T high in this case? He said the refrigeration is maintained at T low, which is actually the source of the heat to the refrigerant. So that means this temperature is T low is equal to minus 35. So that should equal to minus 35. Should be in Kelvin. I have to add plus 273 divided by T high. Where is T high? This is the difference, by the way. We can consider it in degree C in this case. T high, Shabab, is the temperature at which the heat is rejected. Okay? The temperature of the sink at which the heat is rejected to. Is rejected to what? To the cooling water. And the cooling water is coming at what temperature? Is at 18 degrees C and leaving at 26 degrees C. So in this case, the heat is rejected to the cooling water. So the cooling water in this case is the sink at which we reject the heat. If this sink is existing at what temperature? At 18 degrees C. So that should be the value of T high. So the T high is equal to 18 minus T low. T low is equal to minus 35. So minus, don't forget. So it will be negative 35. So it will be positive at the end. Then you can substitute here to calculate the maximum coefficient of performance. It will be 4.59. But he need to calculate the minimum work input for the same heating load, same Q low. So Q low is equal to 5.07 kilowatt. And Q low over work net is equal to this coefficient of performance. Then we can calculate the minimum work input to the system in this case, and it should equal to 1.129 kilowatt. Okay, Shabab? So minimum work input, that means the coefficient of performance is maximum, and I can express it in terms of temperature, T low and T high. He give us T low, but T high, Shabab, is the temperature of the sink at which we reject the heat. We reject the heat to the cooling water. Cooling water is the sink in this case. It's coming at 18 degrees C. So we consider the temperature, the inlet temperature of the cooling water to be as T high in this case, which is 18 degrees C. It is not, Shabab, the temperature of the refrigerant. It is the temperature of the sink at which we reject the heat, which is the cooling water in this case. This is T high. Okay? T low is the temperature not of the refrigerant inside the evaporator. T low is the temperature actually of the food. And if we are talking about a fridge, this is the temperature of the food compartment, which is actually the source of heat to the refrigerant. Okay, so we are talking here about the source. We are talking here about the sink. And that's all for today. So thank you. Inshallah, we'll be meeting next time and we'll start chapter 7.